go bigger? Okay. Right. Okay. Hi. So I'm Jeff, can you hear me? Yeah. Okay. Right. Okay. Right. Is this better? Or I could talk louder. Yeah. Okay. So, right. So I'm going to talk about how to embed a full linear lambda calculus in Haskell. I'm going to give some motivations and then go through a few things and hopefully finish in 20 minutes. Right. So this work combines high order abstract syntax, linear logic, and some Haskell type hacker. At least it's less hacky now than it used to be years ago. So, but it's a nice phrase. So first thing, I'm only really going to try and motivate linear logic. So I know this is more of a Haskell is not necessarily the stomping grounds of linear logic people. So I figured I'd try and give you some reason for learning about it. I'm not going to try and sell it myself. But maybe if you find this amusing enough, you'll go read about it if you don't know about it. So the first thing is that it's a versatile logic, and even the most cursory Google search will let you know that it's useful, and it can change the world, and it's edible. Then if you want to dig a little bit deeper and you go beneath the syntax and semantics, you'll find out that it is a good logic. Which is to say it prevents treason and BS, among other things. Direct quotes, seriously. And it also has a bestiary, which is really interesting, and it's full of real and imagined creatures. And finally, it has real-world applications. It can be used to model voting, and this is serious. There's a project that does this out of Denmark. And I think it's applicable to real estate. Anyhow, so that being said, I'll talk about higher order abstract syntax a little bit. So we're going to start with a simply typed lambda calculus. The context are just sets, right? So there's a hypothesis rule for using your variables, introducing a lambda, eliminating a lambda, and so the core of higher order abstract syntax is essentially that you're essentially transcribing the typing rules into types, and in particular you're going to represent object level variables by meta level variables, right? So here are the typing rules, and now we'll have I'm doing this in the finally titleless style with type class, but the point is really the types of this constant here, right? So this is representing a lambda, and if you look at the typing rule, we've got an A arrow B at some level. Oh, that's the okay, and then you've got the A arrow B, and this sort of becomes just a term of A arrow B. So the idea is that repr here is some type that's going to represent terms of a given type, right? So repr A is going to be some term of type A, and repr B is some term of type B. Okay. And then, so for application, it's the same thing. So you've got a term of type arrow B, right? And a term of type A, and you get back a term of type B. Okay. So now we'll talk about linear lambda calculus. So linear lambda calculus, the basic idea, right, is you can use your variables exactly once. So you have a context, and again, it's a set, except for the linear variable rule, you can only have one thing there, and that's the thing that you can use, all right? For linear functions, you just introduce a linear variable to the linear context. And now for linear application, you have two contexts, and you merge them together. So if you read from top to bottom, this is a non-deterministic merge, right? And what makes this interesting is for typing is if you're going from bottom to top, you have a non-deterministic split. And so if we're going to have an actual implementation of a type checker for linear logic, we need to remove this non-determinism. Okay, so the way I'm going to go about doing this comes from linear logic programming, and it's pretty simple. The basic idea is try what's there, and anything that you didn't use, move on and try and use later. So we're going to have, our context is going to be, it's going to consist of two subcontexts, an input context and an output context, and each context is actually a list, an ordered list. So to represent the LVAR world, we're going to have an input context that has something in it, the thing we're trying to prove, and we're just going to replace that with a box in the output context, denoting that we've consumed that. And the other pieces of the context there are the same. They're unchanged from input to output, right? And then for the Lambda rule, again, we need to, in the original rule, we put this x in here, but we need it to have been consumed, right, because it's a linear variable. So we'll just guarantee that by saying the x that we added to the linear input context, it has to be a box in the linear output context. And then for the application, we're not actually doing any kind of non-deterministic merging or anything. Instead, we're passing everything to the first hypothesis, and we get something out, and then we pass that into the second hypothesis, or premise, I should say, not hypothesis. And what we get out is what we get out in the end. And so this system, this IO system, is equivalent to the previous system that had non-determinism, and there's a proof of this in the paper if you're interested. So now, how do we encode all this stuff in Haskell? Right. So the first thing is to observe that the functions, the variables, linear variables are different, but substitution is the same. So this means, in essence, if we can just teach the type checker how to check for linearity, we can just use regular Haskell functions. So I'm just going to have a new type for linear functions, which is just a regular function. And then, because I'm going to need to have a representation of the linear context, I don't need the actual variables, I just need to know the identities of variables so I can check whether or not they've been used. And in order to get at the identities of variables, I'm just going to use nats. So I'm going to have a nat data type, and then I'm going to have a context, which is either a box or an element. And these are going to be lifted into the type level, right? So then what I'm going to do is my representation for terms, well, they're going to have on it some number, which is the next name for a linear variable, and then the input linear context, and the output linear context, and then the type of the term that's being represented, right? So now the question is, how do we encode linearity? So the first thing is, this is the LM rule, so this rule here. And the first thing to notice about it is we've got here, right, we want to produce a term of this type. And in order to do that, we're going to, since we're using higher order object syntax, we're going to have some function at the meta level, right? And I'll come back to this part in a minute. But the first thing to notice is that in the input context, we have an element B, and in the output context, we have a box. So we've directly encoded what's in the rule that we're representing. But now the question is, what do we do about these things here? And the answer is we look at the variable rule, the linear variable rule. So there is no explicit encoding of linear variables, or variables in general, because we're using higher order abstract syntax. However, this thing up here is a linear variable. And the linear variable rule basically says you need to consume the variable from the context, right? So we can just directly do this. We can say the rule that we want, the type, we can have a type for linear variables, and it basically says, you know, you have a term of type A if, you know, and if the input out, you know, if this constraint holds on the input and output context, which is to say, if you consume a V from the input context and you get output context O, right? So hopefully this will become clear. And so basically we've pushed all the work into this consume. And so the point here is how to define this consume. But before doing that, so this would be the actual rule, the actual term to encode linear lambdas, right? It's a Haskell function that takes as an argument these things, which are linear variables, and returns a representation of something of type B. And then that gives you back a linear term of type A, linear arrow B. Okay, so I'm going to show how to encode consume in a way that works, and then I'll come back to a way that doesn't work, because that's sort of interesting. So I'm going to use multi-parameter type classes and functional dependencies because I have to. And the way I'm going to do it is, you know, I'll have a consume class, and it'll take the target that I'm looking for and an input context, and then it'll give an output context. The idea being that the output context is the same as the input context, except that the target variable has been consumed. Okay, and I'll need a helper class here, and this will just take a Boolean, and then the target, and then the head of the input context, and the tail of the input context, and then the output context. And I'll have to do this because I need to go through the context, but I need to, you know, case on whether or not the head match. Right? So, as I just said, you can consume V in a context that begins with a box if you can consume V in the rest of it, right? And then you can consume V in a context that begins with an element X if this helper predicate holds, where we passed here eq of Vx and V, and I will define eq in a minute, but it's essentially whether or not V and X unify. And then for this consume one, if V and X are the same, which will be the case if this is true, then just return box and I, right? Because the head of the input context match the target. Otherwise, just continue looking and return the element. So hopefully this isn't too terribly hard to follow, but the key to making this work is you have to define an eq class, which makes use of a somewhat old trick for trying to record unifiability. So the idea here is that eq will return true if two things unified, and it will wind up unifying them, or it will return false otherwise. And so for more on why this is done this way and where this comes from, you can look at the original H-list paper from, I think, 2004, 2005. So why can't I use closed type families for this? Because I wanted to use closed type families for this, and it doesn't work. And so if I were going to use closed type families, I would want to just you know, merge the eq and the consume into one type family, one closed type family that looks like this, saying, oh, well, if you're trying to consume a V and you have a V, then great, you're done. And if you're trying, or otherwise, you know, recur, right? And the problem is that I really need some variable V and, you know, S of V. I need that to rewrite. And given the current implementation of closed type families, this won't happen. It'll just get stuck and not choose between the two instances here. And for more on why, I guess I'd be happy to talk about it. I just learned the reasons why, I think yesterday or the day before. But Richard Eisenberg, he can tell you exactly why. And hopefully this situation will change soon-ish. So anyhow, right, so now we can just we can finish the encoding of linear lambdas in Haskell, and you know, a lambda is just what we had before, and an application is just what you'd expect. You know, the function part, the argument, the result. Okay. And so I was just going to show that this is actually, you know, this can work. So right, so if I say here, yeah, okay, good. So that's great. So this is just the code loaded in that I showed before, and it'll tell the type. It gets the right type. There's the A arrow B, right? The A arrow B. And so what if I try and do something, you know, more interesting, and this is not what I wanted, right? Because I wanted this to not type, because X is not being used linearly here. But what happened? And what happened is actually clear here. There are these constraints left over. And so how, you know, is there anything we can do about that? And the answer is yes. I have a notion, there's a notion of a reusable definition. Basically, we have to say that this thing doesn't use we have to say what to do with the context. We have to constrain the context. And so I can just make a definition that says, you know, that the input context is unchanged, right? And then I can have this notion of a definition of something, which just constrains the type in that way. And then I can do what I wanted to do. So if I then this is great. This is not pretty, but great, because you can see that the error message, the top at least, says what's happening. You can't consume something when the input and the output are the same. Okay, so the paper actually includes an encoding of the rest of propositional linear logic. So the rest of the multiplicatives, including the unit. It includes additives, and doing additives requires a non-trivial extension. There's a lot more information you have to keep around. Actually, the complexity class of derivations changes when you add additives to the mix here. And it also includes unrestricted functions. And this is not too hard to do because you can use Haskell hypotheses directly. You just sort of, it's a pretty simple thing to add on. And it's kind of like you have two functions. One of them are just standard higher order abstract syntax, and the other is this stuff with the linear bits. And that's basically it. So in summary, you can have a convenient linear lambda calculus in Haskell. And it's possible that other things can be represented with similar techniques. And there might be a use for this or not. I don't know, but at least it was interesting. So that's all.
The first question that kind of throws itself is that, did you try to encode I/O action with the linear logic?
Did I try to encode what?
I/O actions. Because you now have uniqueness constraint on the real world, don't you?
No, not on the real world. So in order to, so you can write this, and it's DSL, but you have to be inside this repr business. And all of the terms that you can use if you want to have the linearity checks are the terms in the here. So you only get to use these things, and then in the full encoding, all the rest of the terms for the rest of the types. So you have to write in this DSL, and you can sort of you can trivially embed nonlinear stuff in, right? But if you want to sort of take something from the outside but say, hey, it's really linear, then it's not entirely clear what the best way to do that is. So this doesn't actually put any constraints on the real world at all.
So you could basically tell that the real world is a linear variable, wrap it in unsafe for I/O that you do not reveal to anybody else.
You could, yeah, okay. So you could coerce it. Yes, you could do that. I had been looking for a way to not have to do that, but yes, that's possible.
Thank you.
Can you talk about how your techniques related to the techniques like that were used to encode session types in Haskell a couple years back, 2009-ish?
You mean the work by Jesse Toth?
Yep.
That's a great question. So the short answer is no, I can't, because I don't remember the details of that paper right now. I don't think it was a type level encoding that he did. Like, so there were no terms. I actually didn't even give a way to create terms. I only have the class, but no instances. So all of the linearity checking that I showed is the type check. And well, it's the constraint solver. But, and I don't believe that Jesse did that in his encoding. I think it was runtime checks on things.
Okay, and I guess the other question would be, have you considered sort of, you had a pitch at the end for applications, but have you considered looking at sort of session types or references or?
Yes. So one of the things I did actually actively look at was using this to encode a session type calculus. I'm pretty sure it can be done fairly easily, although the operational semantics might be interesting.
One last question. Well, after you. Oh, is there? Did you want to? No, I was going to. Go ahead. Sorry.
So I was curious, this might be a gauche question to ask, but have you looked at the performance? Like the finally tagless should kind of, it all boils away, but I was wondering if you actually checked if it like screws up rewrite rules and that sort of stuff?
I haven't checked. I imagine no, since it's new typed and everything sort of, this, if I gave, so there's a standard way to give an operational semantics to these kind of encodings, and it works for this. And you know, you just strip off the new types and you're left with regular Haskell code, regular Haskell functions.
Sure, but and so a lot of time, I mean, ideally, yes, but because of all the GADTs and stuff like this, sometimes you get coercions are left around that kind of screws up some of the optimization. So I was just curious if you actually, you said, well, here is something that happens to be linear in Haskell versus in the DSL, and kind of compared those two.
No, I have not.
Cool.
It's an interesting thing to think about.
Okay, let's thank Jeff again.